Hello everyone, I'm Neha Mittal and today I'm going to introduce you to vision transformers. This is the outline of my presentation. We'll focus mainly on the VIT architecture, introduce a bit of Swin transformers and a code walkthrough of VIT. The transformer revolution started in 2017 with the paper called Attention is All You Need by Vaswani and al. It changed things for NLP by training much faster and processing a sentence in parallel. Transformers are an active area of research and are doing better with each modification. To quote a line from the paper, the inherently sequential nature of RNNs precludes parallelization within training examples, which becomes critical at longer sequence lengths, as memory constraints limit batching across examples. So RNNs are sequential and their processing in their processing because of which they have memory constraints. Let's look at this example. Let's say we have this sentence that RNN is trying to understand. Mars is beautiful. She is far away. Her mother lives in Bangalore. Now Mars here could be a planet or a person or a pet. Just the first sentence doesn't give you enough information about it or the context of it. So RNN will read the sentence sequentially and try to make sense. The underlying words are in a way output of an attention mechanism that is part of RNN. So when RNN is reading the sentence sequentially, it has to get to the end of the sentence to get some context out of it. So Mars is beautiful, could be anything. She is far away, still could be anything. Her mother lives in Bangalore. So maybe by Bangalore, by the time you have Bangalore in your memory, you have ruled out planet, but still it could still be a person or a pet. So you get, you see that sequential long memory. We had to keep the entire sentence till there to get even little sense of what Mars is. Then let's say this is a very long paragraph and by the end you get to the, by the time you get to the end of the paragraph, the last line reads, Mars is a wonderful human. That is when you've actually resolved the context, right? Now you know that this is a human. This is the problem that Attention is All You Need was talking about. Next, in 2019, this revolution got its tremors in the field of vision with a paper by Google Research called An Image is Worth 16 by 16 Words. In short, it broke the image in 16 by 16 patches, and each patch is treated like a word. And guess how many CNNs are being used in this architecture? You'll be surprised, 0. It's just attention and fully connected networks. Now let's look at some of the state of art in the field of vision. This is image classification on ImageNet, as is clear. And just look at between 2020, like after 2020, 21, how the accuracies are increasing. And on top, you have some derivatives of transformers. Let's look at the top 5. So this CodeNet is convolution plus transformer. There's a new variant. So good news is that convolution CNNs are not completely dead. They're still there. But top 4 at least are all variants of transformers, right? And we've gone, accuracy has gone over 90%. Also, in case of object detection, this is on COCO data set. Look at how fast we are progressing and reaching heights. Top 5 here are all transformers. This is a variant called a Swin transformer, which we will look at very briefly, but later after we understand the VIT. These are the components of transformer from the attention paper. So the main components are encoder, decoder. So here this left block is an encoder and the right block is a decoder. Both of them are fed embeddings. So the embedding is kind of a representation of the input. It gets fed into the encoder. Both of them have these units called the multi-head attention. There are multiple heads and they're paying attention basically. But if you see over here, there are three arrows, all three are coming from the same input. So these are the key, query and value, and they're from the same input in both. The first block of encoder and decoder both are the same. But the second block, the second multi-head attention block of decoder is not self-attention because the input is coming from the encoder. Both have a feed-forward network, which is nothing but a fully connected network, fully connected layer. And then the output of decoder is going through a linear layer and a softmax. Here, if you see carefully, there is NX written over here. In the attention is all you need paper. There is 6 encoders and 6 decoders. So this N represents the multiple of encoder and decoder. Positional embedding here is something that we will look at shortly. This is the flow of a vision transformer for image classification. The input image gets converted to embeddings, which is passed through an encoder, and finally the classification. Let's look at a snapshot of this GIF and understand the blocks in detail. So we divide the image into multiple 16 by 16 patches. Each patch is now sent to a contour layer. The 16 by 16 by 3 patches are flattened, transposed, and added with a class token. Then we add position embeddings. This is the light pink ones, which are again 16 plus 1 weights that are 0 initialized, but allowed to be calculated by propagation. The output of the projection is called the patch embedding. The patch embedding are then sent to the encoder and get the output of each of the CLS token. The representation of CLS tokens are passed through an MLP head to get final class predictions. In CNN, the image was passed through a filter of 3 by 3 or 5 by 5, for example. So each pixel actually got the context from just its immediate neighborhood. Like how the receptive field, the left one is for convolution. So like how the receptive field of CNN was the size of the filter we used. Not completely true, but does give you an idea, right? But here for transformers, the whole image is getting processed at once. So the receptive field is the size of image. Got it? So now let's delve into more detail with an example. And then at the end, we will also go through VIT code to understand it even better. This is our input image, 224 by 224. We split the input image into 16 by 16 patches. This gives us 14 by 14 patches. 224 divided by 16 is 14. And 14 by 14 is 196. So we have total 196 patches. If you think about it, any image whose dimensions are divisible by 16 can be practically used as input to a transformer network. Hence, there is no real limitation to the size of the image used. But obviously the processing will increase, processing time will increase, and there are other complexities also, but gives you an idea, right? Now each patch is 16 by 16 by 3. 3 is the RGB color channel in this case. And we have 196 such patches. Next, we transform these patches to linear form or 1D. One choice for this operation is to use a convolution block such that each patch is passed to it one at a time, and we get output of dimension 196 by 768. So if you look here closely over here at the convolution operation, con 2D 3, 768. So this 3 is the input number of channels, 768 is the output number of channels, and 16 by 16 is your filter size. So if your input is 16 by 16 by 3, and you're passing and your filter size is also 16 by 16, so in this case your output for one patch will be 1 by 768, right? And you have 196 such patches. Hence your output, this output after passing through this linear projection layer is 196 by 768. Right? And there are other ways that people have used to do this transformation. Next, we add the positional embeddings to the patch embeddings and introduce something called as the CLS token or the classification token. Now, positional embedding is used to learn the network based on the position of each patch in the image. So, because in image, the position of each patch is important. They cannot swap so easily and have the same meaning, right? So that is taken care of by the positional embedding. CLS token is prepended to the sequence of patches, and its state at the output of the transformer encoder serves as the image representation. Yeah, so if you look at this, these tiles over here in this drawing, it is interesting to see what these positional embeddings look like after training. So this is trained. Tiles show the cosine similarity. So the top is 1. So yellow means more similar. So if you look across rows, if you look at this 7th row, see how the entire row's yellow is on the bottom, and as you go up in the columns, it's moving up. So it does retain some positional value of based on the image. This is completely learned. Nothing was told to the network as to where each patch is coming from. That is the beauty. Next, this is passed through an encoder, and the output of the encoder is 1 by 768. We are only taking the CLS token part, right? Like I just said, it is the CLS token is the image representation now. This output is passed through an MLP head and finally gives us the image classification. Now let's look into the encoder. The 197, how did it become 197? I don't know if I talked about it. So till here it was 196. Now we've added a CLS token, so this becomes 197. So even our positional embeddings are 197 by 768. So the input to the encoder becomes 197 by 768. It is passed through a layer norm, followed by a multi-head attention layer, and then a residual network. This is again followed by another layer norm, after which there is a MLP block. MLP is nothing but multi-layer perceptron, which is like a fully connected layer. It uses Gelu for non-linearity. In the VIT base architecture, there are 12 such repetitions of each encoder before the output is passed to the MLP head. So something like this. The embeddings go through 12 encoders, then there is an MLP head, and finally the classification. Before we zoom in further into the attention block in encoders, let's understand attention a little bit more. Two of the main components of attention are a key and a query. If we talk in terms of retrieval systems, say a search engine, then the complete database is called keys. The search string or the string you're looking for, that you're searching for, is called a query. The best match results are called the values. Now let's say there is an input image and we split it into patches. This is the query. All the patches together form the key. Next, each query patch, each of these, is compared with all of the keys and we get an attention vector. This basically tells us how each patch is related to the rest of the patches. And it is a matrix multiplication followed by a softmax. Now, softmax basically to contain the matrix values between -1 and 1. So you don't have outliers. If you're multiplying a big number by a big number, it shoots up, right? To avoid that, we do softmax. So now in this example, we have 5 by 5 patches, which is total 25 patches. So there will be 25 attention vectors, right? Because each one attention vector is for one query patch. So in total, we will have 25 such attention vectors. And the next step is to multiply each of these attention vectors, just like we did in filters for CNN. We keep each attention vector on top of the input patches, multiply each, and then add them all. So for one full attention vector, you get one patch, value for one, value of a single patch. So that is how the output is the same size as the input. This is an example of self-attention block used in the vision domain. Given the input features are 16 by 16 patches, we create 3 variants of these inputs: the key, the query, and the value, by passing the input through 3 different 1-by-1 convolutions. Other way of creating the key query value is passing the input through a FC layer. We will look at it when we look at while walking through the code. So we have the key, query, and value. We transpose the key because they're both same dimension. So we transpose key and multiply it with the query. And the output goes through a softmax and we have a attention map, just like we saw in the previous slide. Now this attention map is multiplied by with the value. Again, the value is coming through the input feature map only, the 16 by 16 patches feature map. And the final multiplication is your feature maps, self-attended feature maps. Now let's go back to the multi-head attention block from our previous encoder diagram and fit in what we just learned. The first 3 blocks here are being used to create the key, query, and the value. Now again, if you look over here, we transpose the key, multiply it with the query, do a softmax on the output, multiply the output with the value, sorry about that. And then this value multiplication gives you the output. It goes through another linear layer, and the output of this multi-head attention is same as the input, which was 197 by 768. So this is the complete functionality of VIT. Input embeddings pass through cascade of encoders, then there is MLP head, and finally the class predictions. From the VIT paper, these are the different variants of VIT. The VIT base uses 12 layers, large is 24, and huge is 32. And you can look at the other the values for other variables in the 3 variants. Heads is the attention heads. So it's interesting how reading papers and seeing them out in the state of the art is very interesting. But it's also interesting how it's more interesting to find companies use it. Right, so just give me a second. Let's play this. This was a presentation from the AI Tesla AI Day. Let's look at what they're using.
Function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer to represent this space.
So he's going to talk about this block transformer.
And this transformer, it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values. And then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff. And that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation.
So we all go through these state-of-the-arts, and it does give us confidence in the field, for example. But the true test of any technology is when companies adopt it for applications in the world. So to motivate you further, I'm sharing this clip from the Tesla AI Day. And let's see, they demonstrated what network they're using. Let's see what it is.
Projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer.
This is the part I'm really excited about. You see the transformer over here?
To represent this space. And this transformer, it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values. And then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff. And that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation.
So interesting, isn't it? Just a second. So next, let's speak into Swin transformers. We saw in the state of the art that Swin transformers are catching up better than, especially in the object detection field. I'll just introduce them to you so they're not strangers to you anymore. Why Swin transformers? So one challenge with VIT is that the attention is global. So like we explained, one query gets compared to the rest of the image and to get the attention. This is a very bulky, heavy process, right? So Swin transformers basically attack that part. So in Swin, attention is not calculated all at once, but is calculated in shifted windows. So that is how they get their name, shifted windows, Swin. Other thing is that it is a hierarchical architecture, like the VGG based architectures that we have seen, where um, the output scales up in channel numbers, for example, in the VGG. This is the architecture of Swin from the paper itself. The four main blocks here are the patch partition, linear embedding, Swin transformer block, and the patch merging. In the patch partition, the image is partitioned. Here, the patch partition is 4x4 patches. So the output is h/4. This is the number of patches, right? So however, this is the, yeah, h/4 is the number of patches. 4 is the size of each patch. So 4x4 patches. Then linear embedding is just a normal FC layer to get the output. The size is C, and there are different variations to Swin transformer that are mentioned in the paper. And basically the value of C is different in all of them. Before we talk about this transformer block, let's look at the patch merging. Patch merging is also done through fully connected layers. Here the output has half the number of patches compared to the input, but double the number of channels. So this is the hierarchical architecture that we were talking about. So if you look at the stage 2, the input here, basically these numbers before and after stage 2, the input is h/4 into w/4/c. However, the output of this block is h/8 into w/8 into 2c. So the channels increased and the number of partitions reduced. Same after stage 3 and stage 4. This is how the Swin transformer block looks. Single layer of the VIT transformer is replaced by 2 over here. Rest is mostly same. Ln is the layer norm. Then this is the multi-head self-attention, layer norm, MLP block. So the base is same. But what is different? So here you see a WMSA and a SWMSA. W is for windowed and SW stands for shifted windows. Let's see what that is. So like I said, for attention, we're not computing the attention of the entire image. So we break the image into windows. So let's say the layer 1. So there are 2 layers in the architecture for self-attention. In the first layer, this is how you make 4 different windows. This is the windowed thing. And in the shifted windows, which is the SWMSA, you move this window down by 2 patches. And then there's something called the cyclic shift, which is used to avoid zero padding in this non-overlapping part. And this is how it looks. So this is the shifted window MSA. I think by now you have a good idea of the comparison between the CNN and the transformers. I would just like to iterate that both are evolving fields. It's not the end of convolution, and it is not like everything is going to transformers, but transformers are really, really promising at the moment. And like we also saw, the state of the art combines their combination networks also, CNN plus transformers, or the convolution plus transformers.
Now let's just walk through the VIT code. This code that I'm going to show you is the Hugging Face implementation of VIT. So they've basically taken it from different implementations, and it's a it's a mix of different implementations. You can see references of their GitHubs on the Hugging Face website as well. So I'm going to pick up the main functions that we spoke about today while understanding VIT and show you and explain to you step by step. So let's start with imports. First, we'll do the patch embedding. Patch embedding is when we divided the image into patches, and let's see that again. So this one, we divide the image into patches and we have the 16 by 16 by 3 patches. So let's look at the code for that. First, there is this function called toTuple. What this is doing is converting a single number into a tuple. So our image size is 224, right? So when we call toTuple on that 224, basically what we get as an output is 224 by 224. So I just define that function. I'll call it over here. Image size is 224. So you get 224 by 224 when you call toTuple on image size, which is 224. So again, here patch size is 16 by 16. Number of patches. So number of patches will be the image dimension divided by the patch dimension. If you look over here, they have taken both separately, both dimensions separately, 0 and 1. Basically saying that there can be different number of patches in each dimension, and hence, and also the image size doesn't need to be a square. In our case, number of patches is 14 by 14. Now, next we are just saving these variables, image size, patch size, number of patches. This is the projection. This is the projection that we had seen, this layer, linear projection layer, basically converting the 3D patch into a 2D. From 16 by 16 to 3 by 3 into 1 by 768 in our case. So each of these patches gets converted into 1 by 768. And there are 196 such patches. So our output after projection will be 196 by 768. Now let's look at it with some values. Cont 2D takes first the number of input channels, which is 3. Output is 760. Output number of channels 768. And we will use a kernel size of 16 by 16 because the patch size is 16 by 16 and we are converting into a 1D. So this is a projection. Now in the forward, what we're doing is we're taking a projection on the pixel values. Pixel values are nothing but the input that we have. So batch size, comma, number of channels, comma, height, comma, width. So let's create a random image just to understand things better. So 32 is the batch size, like here. So 32 batch size, 3 is the number of channels, 224 by 224 is the height and width of the image. So this is your input. Now, what are we doing next? We are calling projection on, we will call projection on X. So let's call this Y. And let's see what is the shape of this Y. So this 14 by 14 is because there are so many patches. We are applying it on the input. So now we did convert the image to 768 by 14 by 14, and that is number of patches. All we need to do now is this 14 by 14 becomes 196 and kind of transpose. So that is exactly what is happening over here. We flatten it. When we flatten it, 14 by 14 becomes 196. So let's see that as two different steps. So I will do y equals y. Let's do it as a two-step process. And then I will do y dot shape and y dot transpose y dot shape. But anyway, I messed the values. But after the transpose, the dimension of a vector is 32, which is the batch size, by 196 by 768. That is exactly what we are expecting over here. 196 by 768. Right? So this was patch embeddings. Next, we will add the CLS token, as in concatenate the CLS token and add position embeddings to this. Like we saw, both of these are going to be learned parameters. So here CLS token is NN params, and it is of the size hidden size, 1 by hidden size. Hidden size is 768. That is what we need to concatenate it with, right? Since each of these embeddings are 1 by 768, the dimension of CLS token also has to be 1 by 768. Right? Then we declare this patch embeddings, which we just, the class that we just saw. We take number of patches. Sorry. We take the number of patches from the patch embeddings dot number of patches. And position embeddings is also learnable parameter, and the dimension of this will be number of patches plus one because now we have a CLS token also. So number of patches is 196 plus 197 by hidden size. Then we have dropout and a config. So Hugging Face takes config from a file. You can go to that code again and see. Basically, keeps all this information on the image size and everything. But just for the ease of implementation and demonstration, we have a class over here, which is nothing but the same config. So I call config is equal to VIT config. Let's see what these variables are. Hidden activation, GALU, this is what is inside the encoder. Hidden size is 768, image size 224, intermediate size, we will look at it later. Attention heads 12, number of channels, hidden layers, patch size 16. So this is the config that we will pass when we initialize VIT embeddings. Now let's look at its forward function. First, we are calling a patch embedding. So we get the embeddings like we just saw above. Then the CLS token is getting expanded for the batch size because we need to train each of those batches. All right. So we need a CLS token for each batch. And concatenate CLS token with embeddings. Simple. Then all we do is we add these embeddings. Basically, embeddings is this patch embeddings with position embeddings. And we return them. We do a dropout and we return these embeddings. So if you look at this image again, we are somewhere here. We are exactly here. just before the encoder step. So we have added patch embeddings and position embeddings, and this is what VIT embeddings is going to return to us. Let's just look at the dimensions of this output. So we had created an input random image X. We will call, let's create this VIT embeddings. I don't know if I ran it. Yeah, I did. Let's initialize this config. We'll call it VIT embed. And let's have a look at this. I've not defined it. Right? Patch embedding, inside there is this projection, the convolution that we talked about, and outside there is a dropout. Now let's pass our input through this patch embedding and let's see what the output will be. Embed.shape 197 by 768. So our output over here, or the input to the encoder, is 197 by 768. Let's quickly move to the encoder now. So there are two main parts of the encoder, right? Self-attention block and then the MLP block. Let's first look at the self-attention block. This will give you a better idea of the key query and value concept that we saw, that we went through. So this is the class VIT self-attention. Number of attention heads is 12, which we're getting from the config. Now attention head size will be 758 by 12, which is 64. And all heads is basically all of this, 764 again. Now, like we saw, query is linear. This is the filters basically to get the query key and value. So we are somewhere here. We'll look at let's look at the multi-head attention block only. So there is going to be, so what we are saying is each, the output from the embeddings or the embeddings will be passed through 3 different linear filters, query, key and value, to get the key layer, query layer and the value layer, which is these 3. So in our code here, we are getting these by passing the input to multi-head attention through 3 different linear. So this is for query. So hidden size, comma, all head size. It is same. No transformation here, but we are maintaining. But we are creating, we're passing the same input to 3. We'll get there. So these are the 3 layers that we're going to use, and then a dropout. Now we need to transform all 3 of them to facilitate this multiplication. So like you're seeing over here, we need to get this 12 by 64, right? 197 by 3 by 12 by 64. So let's see how we do that. Let's copy this. Or this, I'll just copy from my reference. We'll try to understand this transpose for scores. Let's try to understand this. Transpose for scores. In this, we are calling, if you look at the forward, transpose for scores is getting called on the key hidden states, right? So key is linear layer, hidden states is 764, 197 by 764. And the output of the linear is basically getting transposed. So let's say, for example, no, not for example, but this X, basically, when we are calling this, the linear layer is not changing the dimension, right? So we are just ignoring that for now. And we are calling the embedding that we got. We are passing that, calling the transpose for scores function through this. So our input was 197 by 768. We did transpose for scores, and now we have 12 by 197 by 64. Basically, we broke down 768 into 12 by 64 and did a transpose. This is what is going to happen over here. So now each key, value, and query layer, these three, are all this same dimension, 32 by 12 by 197 by 64. What's next? Now next we need to take a transpose of K, multiply with Q, pass it through softmax. So let's see, macmul query layer, comma, key layer dot transpose. So we have attention scores. This attention score is passed through a softmax. This is the attention probability. We do a dropout, and then we multiply it with the value layer. This output will be, let's see over here. So the multiplication of K and Q will be 32 for the batch size into 12 by 197 by 197. When we multiply it with values, it will be 32 by 12 by 197 by 64. Now in this next step of code, we are converting it into 197 by 768. So we are going to use view. We create a new shape and then convert our context into that shape. Let's just see what the output will be for this layer. This is the self-attention block. Now, the self-attention block is returning a tuple, but we know it is basically context layer, comma, attention probability. So let's just take, read both and look at their shapes. Context layer here is 197 by 768. So we got the output dimension same as the input dimension. Next, we are going to look at this self-attention output, which is nothing but a linear layer. So we have a linear dropout. That's all. So we pass it through dense and this. Now we just put both of these together, the self-attention block and self-output, and we create a new class called VIT attention. So basically it becomes easier to call them in chain. So all VIT attention is doing is it's creating an instance of VIT self-attention, VIT self-output, and the output of attention is getting passed through the output, and we have attention output. Dimensions are also same. So this is the self output that we just saw. Input features is 768, output is also 768. Right. So now this multi-head attention block is done. Now let's look at the next part of it, of the encoder, which will be the rest of it basically. This MLP block, the layer norm, the residual connections. First, we'll look at this MLP block. So for MLP block, there is a VIT intermediate where we are expanding the dimension. So here is here. So 768 is the input features and output features is 3072. That is exactly what we are doing. That is a 3072 that we had defined before in the config intermediate size. So this 10th layer is expanding the dimension. And applying hidden at the GALU. And then in VIT output, again, we are compressing it back to hidden size, 768 in our case. That's all is happening over here. Now let's put all of this together. We call it the VIT layer. No, I think this is another part. The whole thing together will be the VIT encoder. So VIT layer, we initialize attention, the intermediate that we just saw for expansion, the output, compressing it again, and we have two layer norms, one before and one after. So this is the layer norm before, this is the layer norm after. Coming to the forward block, we get the attention outputs, pass them. So the 0th over here is the output for CLS token, is what we are interested in later for the classification, like we saw. So that is what we are calling as the attention output, and the rest is getting passed as outputs. This is the first residual block. So the input to the encoder is getting added to the output of multi-head attention. Hidden state is the input to the encoder, and attention output here sorry, this 0 is yeah, this 0 is the first output, this context layer. It's nothing to do with CLS token yet. Where was it? Yeah. So this is the first residual attention output plus hidden states. We get the hidden, we are calling it hidden states. Now this is passed through a layer norm after. Then we have the intermediate and output, which is this MLP block, intermediate followed by the output layer. And this is the second residual we added to outputs. Right? Now to form the complete encoder, what we have to do, we have to cascade 12 of these encoders. Which is your number of hidden layers is 12. So here layer is these 12 encoders in cascade. VIT layer. This is the VIT layer. So we initialize the VIT layer with config. Now the code mostly is self-explanatory, not much is happening further in the code. Only that this part, gradient checkpoint and all, this part is for a pre-trained model. So yeah, we're talking about two things in this code. One is this pre-trained model, and the other is the model. So this part of the code is for the pre-trained model. So this is what we are doing. So we have the layer outputs after passing through all the encoders, the chain of encoders. Yeah, this is the chain of encoders. We get here somewhere. Here, this layer output 0 is the CLS token output, basically corresponding to CLS token. So not much. This the later MLP is not happening over here. Then we have VIT model. The next class is VIT model. Yeah, this is the whole thing. So VIT embedding, VIT encoder. Then there's a layer norm and a pooler. Pooler is nothing but another MLP block that is getting used. Yeah, these are embedding, the embedding output pass through the encoder. We have the encoder outputs. Now we take the 0th, which is the sequence output. Did we see the encoder yet? Yes, so this hidden states. It is the 0th, the CLS token output. So that we are calling here as a sequence output, passing it through a layer norm and then a polar layer. Polar layer is nothing but a linear dense layer within activation function of tan h. Let's initialize this encoder and see if we have things working. So let's call it VIT encode is equal to VT. I do not. I have to run some code. I have. Yep, VIT encoder. This one. So I'll just run all. Okay, now it says act to func non-defined, which is in the intermediate list. There's nothing but a function that is given in a different file. I have modified that, and here it is. It's just to parse GLU, the function that needs to be called. Got it. So we have the VIT encoder, VIT embedding. Now Our input was X. We'll pass the embedding through X. We get the embedding output, and that we pass through the encoder. We get the encoder out. Now, encoder out has different outputs. So let's look at, well, let's first look at the type and size of it. So type encode out. Sorry, it's a tuple and it is a tuple of 3. So we will just take the first, which was the sequence out, and look at the shape of it. 197 by 768. This is the output of the encoder. Not the VIT model, right? It is the output of the encoder, the hidden states. Now, after this, there is another class for the classification. That is the final step, correct? So we did this MLP head. No, sorry, we did all of this. Now we are going to look at this MLP head to get the classification output. So let's just go through this class once. This is the VIT model. It's calling the VIT model. And there's a linear classifier. Input is the hidden size and output is the number of labels, which is the number of classes in the class. So in this example, input features is 768 and output, which is the number of classes, is 1000. We get the outputs. We take the 0th output, which is the sequence output, and call the classifier on the output of the encoder. And this is the loss function. So we get the classifier.
That's all from my side. Thank you everybody for listening in. And this is my email ID and my LinkedIn profile. Feel free to reach out.